When an induced current is created in a conducting loop, so for example, due to an EMF that's produced by a change in magnetic flux, as we saw from Faraday's law. So if the strength of this magnetic field is increasing into the screen over time, then the current induced in a loop is going to act anti-clockwise to produce a magnetic field that opposes the change in magnetic flux. And the already present magnetic field is going to exert a magnetic force on the moving charge carriers in that loop. So we saw that was equal to the integral of the current by the cross product of the differential length vector along the wire and the magnetic field vector. So note that when current is induced in a conducting loop, the magnetic forces are only going to be exerted on the segments of the loop that are within the external magnetic field. So in this case, the left half of the loop. So if we consider this point at the bottom of the loop, we have a differential length vector in this direction and a magnetic field vector going into the screen. So you can visualize these vectors as being in the XY plane. And if we're taking the cross product between DL and B, results in a magnetic force that points upwards at this point. And at the top, the differential length vector acts in this direction, and a magnetic field vector goes into the screen. So taking the cross product between DL and B, by the right hand rule, produces a magnetic force vector that points downwards. And by similar reasoning, you'll have a magnetic force pointing in this direction at this point, and at this point it'll point in this direction, and similarly at this point it will point in that direction. So given that the magnetic force only acts on the parts of the loop that are within the magnetic field, we have the magnitude of the magnetic force is equal to the integral of the current, and DL and B are always perpendicular, so we'll have the magnitude of the magnetic field by DL. And a differential length vector along the loop, if we take this as d theta, and we have the radius of the loop, then DL has a magnitude of r d theta. And we can integrate from theta equals pi on 2 to 3 pi on 2, or 0 to pi, and you'll still get the same answer. So therefore the magnitude of the net magnetic force is I pi RB. And by symmetry, the net force on this left half of the loop is going to point to the right. So this will cause a translational acceleration of the loop. So we can apply Newton's second law to a conducting loop moving in a magnetic field as it experiences an induced electromotive force. So what we have is a magnitude of the magnetic force is equal to the mass of the loop by the acceleration. And the acceleration points in the direction of the net force. So the force on a conducting loop is proportional to the induced current in the loop, as we can see, And the current depends on a rate of change of magnetic flux and the resistance of the loop. So recall by Ohm's law, we have the EMF is the current by the resistance of the ohmic element. So if we divide this by R, being the resistance of the wire, we get the current. And note that when this loop gains a velocity, you're going to get a current induced in the loop due to the motional electromotive force. So therefore, when this loop's in motion, we'll have a magnetic force that's acting on a charge in this loop by the cross product between the velocity and the magnetic field. So at every point along this loop, you're going to have the same velocity pointing to the right, because as we saw, the loop is undergoing translational acceleration and a magnetic field vector points into the screen. So taking a cross product of V with B is going to result in a magnetic force pointing in the vertical direction due to the motion of the loop and the magnetic field. And this is going to be the same at every point in a loop that's inside the magnetic field. So this magnetic force pushes electrons in the opposite direction, as the electrons have a negative charge. So that leaves behind positive charge on the other side. And therefore an electric field is produced that results in an electromotive force that pushes current clockwise along the wire.